Thank you for the introduction. My name's Eric. I'm at Duke University. It is a pleasure to be here. And I'm really excited to talk about this topic for three reasons. First of all, I do research on it. Anyone who does research is probably kind of obsessed with whatever they're working on. Number two, there are a lot of misconceptions about this topic. And then number three, things are really coming full circle because the first paper I ever published was in the ISSN's journal, and it was about metabolic adaptation. And that is basically an adaptive reduction in energy expenditure when we restrict caloric intake. Now my research has taken me to a different side of the same coin, which is compensating for really high levels of physical activity by reducing other components of energy expenditure. So, like I said, I'm at Duke, and I have probably the weirdest set of affiliations you can imagine. I'm in evolutionary anthropology, and I'm also in the religion and social change lab. So when I go to a department meeting, I don't know if we're going to be talking about political polarization in the Methodist Church or the morphological evolution of the talus of lemurs. It literally could be either one. So that keeps things fresh. But today we're talking all about total daily energy expenditure. And when we talk about total energy expenditure, we can break that down into individual components. So we've got basal or resting metabolic rate, which makes up usually a pretty significant chunk of it, usually 60 or 70%. There is a technical difference between basal and resting energy expenditure, but for today's purposes, we can treat those as fairly equivalent. We've also got the thermic effect of feeding, which is usually only about 10% of our total expenditure. That's just the calories that we burn in order to kind of chew, digest, break down, metabolize the energy that we're consuming in our diet. Of course, we've got exercise activity thermogenesis. Those are the calories burned during structured, intentional exercise. And it's really difficult to put a percentage number on that because it depends, right? You could be an ultra marathoner and that number is going to be really big, or you could be me sitting behind a desk most days and that number is going to be pretty small when framed as a percentage. And then finally, we've got non-exercise activity thermogenesis, and that basically pertains to just the calories we burn when we're not resting or not in complete rest and not doing structured exercise. So maintaining posture, fidgeting in a chair, going to check the mailbox, things like that fall under non-exercise activity thermogenesis. Now, if you're an athlete and you're trying to fuel your training, or if you're trying to gain weight or trying to lose weight, trying to change your body composition, it's very useful and important to have a decent understanding of your total daily energy expenditure so that you can set a calorie target that's appropriate for your goal. So normally, the way people will do this if they don't have access to a lab and a bunch of measurement equipment is they will try to estimate with equations. So you can see a bunch of different equations on the slides right now, and these will get an estimate for basal or resting energy expenditure. And you can see some of these equations use just fat-free mass. Other ones will use things like weight, height, and age and biological sex in combination. And really what those are doing is trying to essentially guess how much fat-free mass you have. So it really comes down to whether or not you have a decent measurement or estimate of your fat-free mass. But ultimately, these equations that predict or estimate resting metabolic rate are very much focused on your fat-free mass. And that's good because fat-free mass is kind of the biggest single predictor of resting energy expenditure. But there is a bit of a challenge when it comes to using these equations. First of all, fat-free mass is the biggest individual predictor of resting metabolic rate, but it's certainly not perfect. And then the bigger issue is that when we make the leap from resting energy expenditure to total energy expenditure, we have to account for those other three components beyond the resting metabolic rate number. When we start to look at the relationship between fat-free mass and total daily energy expenditure, we see a tremendous amount of variation in calories burned per day, even at the same level of fat-free mass. So obviously, we need to figure out how we're going to go from fat-free mass to total daily energy expenditure. Part of this variation is due to differences in resting energy expenditure, but a big portion of it is due to differences in activity level. Someone who has 60 kilograms of fat-free mass, whether they're very active or very sedentary, we might expect that to have a meaningful impact on their total daily energy expenditure. So usually, again, the typical approach, if you don't have any measurement devices, is you're going to rely on a correction factor. So you use one of those previous equations to estimate your resting metabolic rate, and then you multiply by a correction factor based on your overall physical activity level. So if you're very active, you might multiply that resting metabolic rate estimate by 1.9. If you're extremely sedentary, perhaps you multiply it by 1.2, and most people will choose one of those categories in between. So when we boil it down and we think about how this general approach works with using these estimation equations, there is a pretty big assumption that is inherently baked into the process. And that is the idea that the effect of physical activity on energy expenditure is additive in nature. And so what that means is, as we go up from one level of activity to the next, we would expect a fairly linear increase in total energy expenditure. So like I said, we're just kind of applying one of those really simple correction factors based on your perceived or kind of self-reported physical activity level. And there's no real gradation or complication here. The more exercise you do, the more total daily energy expenditure goes up. And again, the relationship is fairly linear. That's at least the assumption built into this equation process. And that's really the focus of today's presentation is on how certain are we that that actually is a safe assumption? Of course, it's very intuitive. We know that exercise burns calories. Intuitively, we would expect that more exercise burns more calories, and that's pretty much as simple as it seems. But exercise energy compensation introduces this idea of a constrained energy expenditure model. So on the left of the screen, you see the additive model, which I just explained. It's very simple. The more physical activity you do, the more total energy expenditure goes up in a linear fashion. The constrained energy expenditure model is really the main focus of the lab I work in with Herman Poncer at Duke University. The idea is that when you go from extremely low levels of physical activity to maybe light levels of physical activity, we do see a fairly linear increase in energy expenditure. But when you start to get up to really high levels of physical activity, we start to see that relationship level off a little bit. It seems like energy expenditure in totality is being constrained or being limited to some kind of ceiling effect. And in order to make that happen, as you're doing more and more physical activity, there must be some compensatory adjustments that are reducing other elements of energy expenditure, perhaps resting energy expenditure and perhaps non-exercise activity energy expenditure. So really what we're looking at here is two contrasting models that are contradictory in nature. The very simple additive model, which is usually the gut instinct or the kind of intuitive assumption, and then the constrained model, which suggests that we actually are adaptively kind of reducing energy expenditure to account for very high levels of physical activity. Now, in our lab, we measure energy expenditure using something called doubly labeled water. And doubly labeled water takes advantage of those old chemistry equations we used to do in biochemistry talking about metabolism. So when we break down macronutrients for energy, of course, we get ATP in the process of doing that. But what we do is we consume oxygen in the process and we yield both carbon dioxide and water as, kind of byproducts of this process of metabolism. And so what's interesting is that we will see both the production of, we'll see carbon dioxide, which obviously has oxygen, and then we'll see water production, metabolic water, which has oxygen and hydrogen. And the reason I highlight that is because doubly labeled water takes advantage of that relationship in terms of breaking down energy and producing both carbon dioxide and water. So what we do with doubly labeled water is we label water twice. That's why it's doubly labeled. So we will label water with a heavy isotope of hydrogen and a heavy isotope of oxygen. And you can see the equation at the bottom of the screen. What we're looking at is, when we look at the elimination of that heavy oxygen isotope, that's going to be eliminated through water and carbon dioxide. But when we look at the elimination of the heavy hydrogen isotope, that will only be eliminated through water losses. And so by looking at the elimination of these two different heavy isotopes, we can work our way back through calculations, look at carbon dioxide production, which ultimately allows us to estimate energy expenditure. Now, You might be wondering why we bother. That sounds like a lot of chemistry and work, and it's also very expensive relative to just taking, a quick measurement with indirect calorimetry or something like that. The real benefit here is that we can examine energy expenditure in totality rather than looking at just resting expenditure, which is often done with indirect calorimetry. And we can look at it over maybe the course of a week or so when someone is doing their normal daily activities. So we can give this to a marathon runner, have them do a week of their normal training, and we don't have to worry about guessing how many calories they're burning during exercise versus rest. We get a nice number for their total expenditure as they go about their day-to-day life. So, with the constrained energy expenditure model, like I said, the idea is that as physical activity gets higher and higher, we see compensatory reductions in maybe resting and non exercise elements of energy expenditure. So, if the constrained model holds true, we would expect that higher levels of activity energy expenditure would be associated with lower levels of basal energy expenditure. And there's a recent paper, recent 2021 by Carreau and colleagues, where they looked at the doubly labeled water database. There's a huge open access, you have to apply to use the data, but there's a big kind of repository of doubly labeled water data from several different studies. And they utilized that data to observe this relationship where there was a negative correlation between activity energy expenditure and basal energy expenditure. Now, if this was the only evidence for the constrained model, I would not be super convinced. However, there is additional evidence that I think is potentially even a little more compelling. So this is a figure from a paper by Ponser and colleagues in 2016. What we're looking at is the relationship between total daily energy expenditure measured via doubly labeled water, and then on the x-axis, we have physical activity measured via accelerometry. And this was from 5 different cohorts, and each cohort was at a different level of what we would call industrial development. So ranging all the way from essentially hunter-gatherer type economic models all the way up to very sedentary American cohorts. And what they found was, as the constrained model would predict, when you go from extremely low to kind of low physical activity levels, we do see a somewhat linear increase in total expenditure, but that actually plateaus relatively quickly. And you see when you're looking at these different box and whisker plots for each decile of physical activity, the 7th, 8th, 9th, and 10th are pretty much falling essentially on a straight line there. So we see that relationship with physical activity and energy expenditure really starts to get constrained at higher levels of activity. And one observation that's really striking, the black bar in each box represents the median for each decile. And when you look at the energy expenditure median values, they are really quite constrained within these very diverse cohorts, where you see the median value within each decile ends up being really in the 23 to 2,500 calorie per day range, which is a really striking level of homogeneity in terms of those median values. So, like I mentioned, I'm affiliated with the Department of Evolutionary Anthropology. So we often approach our research through the lens of, evolutionary advantage or disadvantage. This is on the screen here a model representing the dual intervention point model by Speakman and colleagues. And the idea here, this pertains to the regulation of body weight or body fatness, adiposity. The idea is that, back in the day, people would talk about defending a body weight or a body fat set point. And the issue with the body fat set point model is that it doesn't leave a lot of room for environmental factors and behavioral factors. It's kind of purely biological and very restrictive in application. The dual intervention point is kind of a derivative of that model that suggests we want to maintain our body fat within a reasonable working range. We don't want body fat to get too low, as obviously that introduces the threat of starvation. We also don't want body fat to get too high, as in terms of evolutionary perspectives, that would potentially be disadvantageous for locomotion for daily activities we need to survive, and also could increase the risk of becoming prey. Back when that was a little bit higher on our priority list, was not getting eaten. So what this model suggests, kind of intuitively, I would say, is that we must have some levers to pull where we try to defend specifically this lower intervention point. If we had no mechanism to constrain energy expenditure, then we really wouldn't have much of an ability to defend that lower intervention point other than just having greater hunger cues when we are in a large energy deficit and body fat starts to get low. So when you view this idea of constrained energy expenditure through an evolutionary prism and with this dual intervention point model in mind, you can imagine that one of the levers, one of the mechanisms we have to avoid really precipitous drops in body fat is perhaps we can alter our energy expenditure with some compensatory mechanisms. And from an evolutionary standpoint, you could imagine that if you were a hunter-gatherer, your times of the highest physical activity would likely be scenarios where theoretically resources were fairly scarce. You might have to cover more ground trying to hunt or gather for resources when caloric resources in the environment were quite low. So you could kind of weave together an idea of how this might be advantageous from an evolutionary perspective. But the ISSN, we're not really that into evolution, at least in terms of research focus. We want to talk about athletics, right? Talk about sports nutrition. So this was a paper by Thurber and colleagues, and they looked at energy expenditure in a variety of different athletic pursuits, ranging from Tour de France cycling to Race Across the USA, which is doing a marathon every day for several weeks all the way across the country, Arctic trekking as well. And so what's really interesting about this is we like to frame energy expenditure in terms of metabolic scope as our units. And it's really simple. Metabolic scope is your basal metabolic rate, or it's your total daily energy expenditure divided by your basal metabolic rate. So if your basal metabolic rate is 1,500 calories per day and you're burning 3,000 calories per day, your metabolic scope would be 2. 3,000 divided by 1,500 is 2. Now, in really short events, so less than 0.1 days, we can see metabolic scope values above 15. For a short period of time, you can get your energy expenditure basically as high as you want or as high as you're willing to push. Now, we do see that drops off a lot when we start getting into events that are more than half a day. So if you look on the left side of the screen, you can see once events are more than half a day in duration, we see a pretty precipitous drop in the metabolic scope that's observed. And if you look on the right side of the screen, this is where we see really long duration events. And we start to see that for a short period of time, you can push through and reach really high metabolic scope values. But as time goes on, it seems like habitually, it's extremely uncommon to observe metabolic scope values above 2.5. And so you see over in panel C, from all these different data sources, from all these different athletic events of varying duration and incorporating pregnancy data, which is a very energy intensive, long duration physiological event. It seems like for now, until we can disprove it, and we're trying very hard to, it looks like 2.5 seems to be some kind of ceiling level approximately when it comes to how much energy expenditure someone can maintain for an extended period of time. And so this is more data from the Race Across USA, which, like I said, was basically a marathon a day for several weeks. And what's interesting is that in week 1 of this event, the difference between observed energy expenditure and predicted energy expenditure was pretty close to 0. People were burning as many calories as we would expect. But in the final week, when those measurements were repeated, the researchers, Thurber and colleagues, found that there was actually quite a large discrepancy between predicted energy expenditure and measured energy expenditure. And the drop ended up being about 600 calories per day. So that's a very precipitous drop that seems to reflect a longitudinal adaptive reduction in total daily energy expenditure from trying to maintain this really, really high energy expenditure for a prolonged period of time lasting several weeks. One other thing, of course, very high levels of physical activity seem to impact energy compensation. Another thing that seems to impact it is energy balance. This is a really fantastic paper by Willis and colleagues. And what they found was that, again, this is the same kind of plot looking at deciles of physical activity against total daily energy expenditure. When you look at folks who are in neutral or positive energy expenditure, and these aren't athletes, these are folks kind of general population, we really don't see a whole lot of energy constraint. there seems to be a fairly somewhat linear increase in energy expenditure as physical activity goes up. But in these folks who generally aren't super active, we do see fairly considerable constraint being observed when they are specifically in negative energy balance, which basically means that they are in a caloric deficit, eating fewer calories than they burn on a daily basis. So I think the two really important things to note here is this has implications when it comes to athletes trying to figure out how many calories they should consume. It also applies to weight loss scenarios when people are in negative energy balance and are wondering, why do I have to diet on such low calories? I'm doing all my exercise and I'm not losing as much weight as I thought. It's very possible that this could be playing a role in those types of observations. So one of the biggest misconceptions about this topic is that when we talk about constrained energy expenditure, sometimes people think we're saying that athletes don't burn any more calories than sedentary folks. And that's not at all what we're saying. So the evidence is really clear from doubly labeled water studies. Athletes do burn considerably more calories than a sedentary individual of the same body size. So rugby, soccer, basketball, you can see the estimates on the screen. We're not saying that exercise doesn't increase energy expenditure flatly. What we are saying is that the relationship is actually quite complicated and that there are some compensatory mechanisms by which we can constrain non-exercise elements of energy expenditure in certain scenarios, such as very high levels of physical activity or negative energy balance. And this is from a study by Brodsky and colleagues where they found that exercise alone with no diet intervention was really not very effective at all for inducing fat loss. And surprisingly, total daily energy expenditure didn't increase as much as they predicted from the prescribed amount of exercise. And this is pretty on par with most of the literature that we see, which is when you try to induce weight loss, specifically through exercise, usually it doesn't pan out quite as well as you would hope. Energy expenditure doesn't increase quite as much as you would predict, and fat loss doesn't really occur to the degree that would be predicted mathematically. So the idea with exercise energy compensation is that we experience compensatory reductions in other components of energy expenditure when exercise energy expenditure increases. So putting that quantitatively, if we increase our cardio by 100 calories per day based on mathematical predictions, our total daily energy expenditure may only increase by maybe 50 or 70 calories per day. So the magnitude of compensation, and Joey, I'm wrapping up real quick here. Average compensation is usually about 30%. So instead of increasing your energy expenditure by 100 calories, maybe it only goes up by 70. But depending on different scenarios, in terms of your body fat, your activity level, your energy intake, compensation may be as high as 50%, or it could be quite minimal. And then, of course, we have metabolic adaptation that you can also layer onto this. Don't have time to get very deep into metabolic adaptation, but that paper's in JISSN. Highly encourage you to read it. But the moral of the story here is that when people are confused about how many, why their caloric expenditure is lower than they thought it should be, it could be due to exercise energy compensation. It could be due to metabolic adaptation, and it could be due to a little bit of both. And so the maximum impact that we might see in total daily energy expenditure could be a compensatory reduction that's somewhere in the ballpark of 600 to 800 calories per day. So wrapping up, I want to thank the authors of all the papers I cited, the participants of all the studies, colleagues past and present, Joey and the ISSN. It is absolutely a pleasure to be here.